All right, let's jump right into it. Today, we're embarking on a bit of a scientific detective story in this explainer. We're traveling out to the dark, remote, freezing edges of our solar system to investigate an absolutely massive planetary mystery. You see, Uranus and Neptune, our two ice giants, have been hiding some pretty wild secrets deep beneath their clouds. We're talking about secrets that generate some of the most bizarre and chaotic magnetic fields ever observed in the universe. So we're going to break down the clues, peer straight through the layers of these giant planets, and discover a totally strange, glowing state of matter that actually solves the case. Let's get started.
To really understand just how weird things are out there, we have to start with what we know best, right? Earth. Our home planet has this beautifully neat, axial, dipolar magnetic field. It basically works like a giant bar magnet that's aligned pretty closely with our north and south poles. Very orderly. But the ice giants? Oh, they throw all of those rules completely out the window. Their magnetic fields are non-dipolar and non-axiosymmetric. In plain English, that means they're totally chaotic, wildly off-center, and misaligned from their rotation in a way that literally perplexed scientists when Voyager 2 first flew past them back in the 1980s.
Okay, let's dive right into this. The main axis of Neptune's magnetic field isn't pointing up and down like ours does. It's actually tipped over by a massive 47 degrees compared to the planet's axis of rotation. Just to put that into perspective, imagine if Earth's magnetic North Pole was suddenly somewhere down near the equator. That's the kind of extreme misalignment we're talking about here on Neptune.
And Uranus? It's even more extreme. Its magnetic axis is tilted about 60 degrees from its axis of rotation. Because of this staggering misalignment, as these planets rotate throughout their day, their magnetospheres undergo wild, chaotic variations. It's a constantly tumbling, incredibly unstable magnetic environment. It's completely unlike the steady, reliable shield we enjoy here on Earth.
And here's the real kicker. This chaotic tumbling field isn't weak, not at all. In fact, the magnetic field of Neptune is roughly 27 times more powerful than the magnetic field of Earth. So think about that. We have a magnetic structure that is completely lopsided, wildly rotating, and just incredibly strong.
So what does this all mean? This brings us to the central mystery of our explainer. Why on Earth, or rather why on Neptune, does a planet made of ice generate a magnetic field that goes through such wild, chaotic variations every single day? We know that magnetic fields are generated by the motion of conducting fluids inside a planet. So to find the culprit for this huge magnetic anomaly, we can't just look at the surface. We're going to have to travel deep, deep inside these alien worlds.
Part 1. Descending into the ice giants.
Before we even get inside, we have to navigate a truly extreme environment, and this brilliantly illustrates just what we're up against. Neptune is our solar system's windiest world. Despite being so far from the sun and getting very little energy, its outer environment is just brutal. Earth's most powerful winds hit about 250 miles per hour. Jupiter's can get up to 400. But Neptune? It features literally supersonic winds whipping at almost 1,200 miles per hour. Voyager 2 actually tracked a massive storm called the Great Dark Spot, which was large enough to swallow our entire Earth, spinning at these staggering speeds.
But as we sink down below those supersonic freezing methane clouds, we don't actually hit a solid icy surface. Actually, scratch that whole solid planet idea. Over 80% of Neptune's mass is made up of a hot, dense fluid of what scientists call icy materials. It's a mix of water, methane, and ammonia. If you were picturing a nice ocean of liquid water, think again. Down here, it's a super hot, dense fluid that doesn't boil away simply because the incredibly high pressure keeps it permanently locked and crushed inside. If we look closely at the interior composition models for both Uranus and Neptune, you can see they follow a very distinct three-layer structure. It's like a giant puzzle. On the outside, we've got an envelope of hydrogen and helium gas. But look at that massive middle section that spans so much of the planet's radius. As we travel inwards, the molecular water transforms. We hit this huge layer of ionic water, and then, deeper still, a thick shell of something called superionic water, all surrounding a relatively small, rocky core. The sheer volume of water inside these planets, that's the absolute key to our mystery.
Part 2. The clues in the ice. Phases of extreme water.
So, as we descend, the water goes on this crazy chemical journey. It starts as normal molecular water, the kind where hydrogen and oxygen are bonded together like we're used to. But as the pressure and heat rise, it breaks apart into an ionic fluid, which is basically a soup of charged particles. Finally, at the deepest layers right before the rocky core, it goes through a radical phase transition into a highly exotic state, the superionic phase.
Now, what's really interesting about this mapping of water against temperature and pressure is where those black and white lines fall. Those lines represent the actual conditions inside Neptune and Uranus. And you can see how they slice right into that dark blue region labeled superionic. When temperatures soar past 3,000 Kelvin and pressures hit millions of bars, millions of times the atmospheric pressure you're feeling right now, the water literally has no choice but to take on this bizarre superionic form. So what exactly is superionic water? Well, it's a hybrid state of matter. Picture a rigid crystalline structure made entirely of oxygen atoms, but it isn't solid ice like we know it on Earth. The hydrogen atoms, the protons, detach completely from the oxygen and flow almost freely through that oxygen lattice, just like a liquid. It's kind of like a solid oxygen scaffolding that's glued together by a flowing river of electrically charged protons. Totally wild, right?
So the crucial point here is how this incredibly strange material actually behaves in practice. Advanced simulations show that despite having a solid oxygen lattice, those free-flowing protons give the superionic phase a viscosity of roughly 1 millipascal second. In simpler terms, it responds to stress almost exactly like a fluid. Plus, because those protons are electrically charged and flowing freely, this superionic ice is highly electrically conductive. And finally, this dense material forms a stably stratified layer deep inside the planet. That means it settles into distinct, stable layers that don't mix easily at all with the fluid sitting above it.
Okay, so let's recap. We now have an electrically conductive, fluid-like layer of glowing hot, high-pressure ice sitting deep inside these planets. So how does this extreme superionic ice actually solve our initial mystery? How does it explain a magnetic field that is tipped on its side, completely off-center, and 27 times stronger than Earth's?
Part 3. Solving the case, the superionic dynamo. Let's contrast how these magnetic fields are built. Earth's magnetic field is a neat dipole because it's generated deep down in a central convecting fluid iron core. It's very symmetrical. But detailed 3D simulations of Uranus and Neptune reveal a totally different geometry. Their chaotic, non-dipolar magnetic fields can only be produced if they are generated in a very thin fluid shell. We're talking at most 0.3 planetary radii thick. And this thin shell has to sit above an inner region that is fluid but stably stratified, meaning the deeper fluid itself is trapped in those stable, rigid layers we talked about.
And this is exactly where our superionic water acts as the perfect puzzle piece. It really hits the nail on the head. The location of the superionic layer begins right where this thin shell dynamo requires a stably stratified inner region to be. The ionic water fluid layer above it acts as the thin convecting shell generating the field. The heavy superionic water underneath acts as a stably stratified barrier that actually prevents a uniform Earth-like convection, and that is what forces the magnetic field into its chaotic, off-center shape. And because the superionic phase is a highly conductive protonic fluid, it perfectly explains how this strange dynamo can pump out a magnetic field 27 times stronger than our own.
Which leaves us with a truly mind-bending realization. You know, when we look up at the night sky and think about water in the universe, our minds almost always immediately go to liquid oceans. But when you consider just how many Neptune-like exoplanets exist out there in our galaxy, the most abundant phase of water in the entire universe might not be liquid at all. It might just be glowing, scorching hot, superionic ice, hidden under crushing pressures, silently powering these chaotic magnetic shields across the cosmos. Thanks for joining me on this explainer.